In this video, I'll show you how to forecast anything using the same technology that drives ChatGPT, namely transformers. Rather than predict a continuation of words, we'll be forecasting a continuation of numbers, which could represent traffic data, weather, or financial patterns. Up until recently, it's often been better to use a simple model, perhaps just a simple linear model, when forecasting rather than using transformers. But that has changed within the last few years, and now there's very good performance from models such as PatchTST and Chronos. I'll walk you through how those two models work, how to make forecasts, and how to prepare data to do a custom fine-tune for your application. In terms of video overview, I'll start off by briefly describing how time series forecasting works. Then I'll describe the PatchTST model and the Chronos model. I'll give a comparison of these two models and why you might want to use one or the other in different cases, before then giving a demo of how to forecast with PatchTST and how to do fine-tuning, and the same then for Chronos. What is time series forecasting? It's easiest to look at an example. Here I've got the demand of the Irish electrical grid, and the y-axis shows the load in megawatts going from 3,000 to 5,000. The x-axis shows the progression of that load over a week. You can see it oscillating from day to night here with a pattern of 7 different peaks. Now, in the case of forecasting, what we want to do is feed in a pattern like this and then predict the continuation. And while this is for electrical demand, the methods I'm going to show you apply generally, and the models apply generally across many different time series problems, whether that's predicting traffic, predicting prices, predicting maybe different aspects of pollution. Any case where you have some linear time series and you can have a continuation, you can consider using one of these forecasting models. To break it down into very simple terms, you can think of some input data points, and they are going to be evenly spaced because that's what the models today will require. If they are not evenly spaced in time, you could interpolate or extrapolate perhaps to generate an equally spaced time series. It can be hours, days, any type of time gap, provided that it's uniform in time. And you'll have an input series that then the model is going to try and give you a prediction for the follow-on output time series here. And depending on the model, either there'll be a fixed number of points that are predicted here, which will be the case of PatchTST, often it's 64, or in the Chronos model, we will predict these outputs one at a time. So we'll predict the first, we'll pass it back in as an input, predict the next, the next, the next. That's known as an autoregressive model. That's also how the language models today work. And that will allow you to keep decoding as far as you like, understanding that as you go further out, the accuracy is going to decrease. So now I will describe the PatchTST model, which gives a fixed number of forecasts, and then I'll describe the Chronos model. Here is the architecture of PatchTST. I'll break it down into portions. Starting off, it's useful to identify here the input time series. So here might be the electricity demand for different points along a week, evenly spaced. And here are the output predictions of the next 4 points here. And as the name suggests, PatchTST, there is patching involved in how this model works. Namely, it takes a bunch or a little patch of the inputs, and it will pass them through a linear layer that combines them into a single vector. So there's one vector that ultimately represents a patch. And here, if we have this many inputs, which I think I have 18, that'll be converted, that's a patch size of 6, into three vectors after going through the linear layer. Now, there's also a position embedding added. What that means is we transform through trainable matrices the inputs here into a single vector, but we also concatenate or add on a position. So this will say position 1, position 2, position 3. And that numerical encoding for the position just gives the model a sense that there is an order to the data that is going in here. These vectors then are transformed through transformer layers that include attention. So we have the input patch embeddings converted into the transformed patch embeddings. And all of these transformed patch embeddings are passed through another set of trainable matrices to then provide in one shot the output predictions for the number of set output timestamps. Notice that this is all single pass. We are not passing back the outputs to the input and iterating around autoregressively as is done in language models. Also notice that there are no tokens. We have numbers here that are coming in. Yes, they may be normalized, but they're still continuous numbers. They are then converted into embeddings, which is still numbers. And the predictions that are made here are also going to be in the form of continuous numbers. Now, let's move to the Chronos model. And before I describe the architecture, I just want to talk about the normalization and the quantization, because Chronos uses tokens, and to get tokens, you need to quantize the input numbers. So the first step before quantization is normalization. This is a normalized version of the graph I showed you before. Quite simply, I've divided by the interval mean. So I've taken the mean, divided all the points by that, and now the mean of this graph is 1. And you can see oscillation about that point. And this is commonly used in training time series models because it means you can use a wide variety of data normalized to train the same model, which means you have much more data to train the same model. So that's normalization. And once we normalize, we then quantize. And this involves splitting the values here into a number of buckets. So here I've split them into 15 buckets from 0 to 14. And with this amount of buckets, it looks jagged, which is good for illustration purposes here. But in practice, you would use many more buckets, often more than 1,000, so that this looks smooth. But the reason for using the buckets or bins is because each of these buckets or bins is now like a piece of vocabulary. It's like one token in your vocabulary. And you can see now the analogy to a language model. In a language model, you might have a token for each word, but here we've got a token for each of these value buckets. So we're able now to run the model in the same way we would a large language model. We take in the input time series, normalize and quantize it, and now each of these inputs is a token. It'll be a token if there are 15 quantization levels. It'll be a token either 0, a token 1, a token 3, a token 4. And these tokens then, as in a language model, go through an embedding layer and they're converted into vectors. Now here I've only shown 3 points, but actually there will be an embedding for each of these tokens. And each of the embeddings will then be converted through the transformer layer into a transformed embedding. And these transformed embeddings will then be converted into a softmax to give a probability distribution. Well, they'll be subjected to a softmax to give a probability distribution over those buckets or bins. So what this gives us is a probabilistic output for the next step, a probabilistic representation of the next step. Basically, we have these time inputs. They're all in buckets, and we're trying to predict which bucket is the next output going to be in. Is it going to be in bucket 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 14. Then we take this output and we pass it back to the input like this here, and we run forward again. We take that, we run forward again. We take that, we run forward again and again. So you can see this is an autoregressive model because we are constantly calculating the next forecast, bringing it back to the input and calculating the next forecast again. So unlike PatchTST, which is once through, to get a series of forecasts, we need to autoregressively run this model, which is going to take more time. And that is one of the key differences between PatchTST, which is fast and once through, and Chronos, which is slower because of that autoregressive nature. And also Chronos happens to just be a larger model, which will make it slower as well. Now, on a technical note, I've shown here a decoder-only architecture like GPT-2, GPT-3, and there is a version of Chronos available that's a GPT-2 type architecture. But actually, the more commonly used one is the T5 type architecture, which is an encoder and a decoder. And in that architecture, there is a separate transformer for the input layers. So you can think of it a bit like this here. There would be an encoder, and then you can think of there being a decoder, something like this here, that takes as input any of the decoded tokens, the green ones here. Maybe I could just call this decode, something like that. And this would be here encode. And if you go to decoder-only architecture, the prediction model head will actually only be over the decoder. So I'll just type in here the softmax. And actually the outputs of the encoder, rather than them going to the softmax, the outputs of the encoder would actually go to the decoder like this. So they would also be treated as inputs to the decoder, something like this here. So this, what I'm showing you, is the difference between a decoder architecture and an encoder-decoder architecture. So here you have the embeddings, but the inputs go to the encoder, whereas the decoded inputs, the ones that come back around, they go into a decoder here. And why would you have this? Well, the thought is you have specialization. Basically, this encoder is well able to handle these inputs here. It's familiar is familiar with accepting a long input sequence, whereas the decoder is familiar with receiving these tokens that go back around. Now, in practice, it turns out decoder only has kind of won out, and most of the models today are decoder only. But maybe for some applications, particularly with smaller sizes, you can find advantages and better performance empirically from the split encoder-decoder architecture. In any case, Chronos is mostly using the T5 architecture. It's a Google language model that is encoder-decoder. It comes in multiple sizes. So if you look at the Chronos model on Hugging Face, I'll put a link in the description. You can see there are 5 sizes here from tiny up to large. And they match the sizes of the T5 models from Google. So it's a nice suite of models because you can start off really small with just 8 million parameters, and you can go up to something that's quite a bit larger. For example, if we look at the T5 model here, I expect it'll be about 3 gigabytes in size. Yeah, 2.8 because it's in 32 bits. So 700 megabytes in size. 700 million parameters in size times 4 then, because there's 8 bits per byte. So if it's 32 bits, that means roughly times 4. So that's why you're getting close to 3 gigabytes in size of weights. But if you have the smaller model, which is just, let's see, 8 million parameters, then that's going to be only about 32 megabytes of size. So not that big a model. PatchTST is only about 2 megabytes, I think. So that's an even smaller model. But yeah, T5 gives you this control of going to bigger models if you want to have better performance. Now, before wrapping up in the slides, I'll just highlight a few differences between PatchTST and the Chronos models. As I said, PatchTST is patch-based, whereas Chronos is autoregressive. It's not patch-based, and it is autoregressive. PatchTST is patch-based, but it's once true. The model size we've already talked about. In terms of zero-shot capability, which means just taking the model off the shelf and then using it for inference, the Chronos model is going to be quite a bit stronger. It performs very well on a custom application, even with no training, whereas the PatchTST performance is not going to be quite as good. The forecast horizon is fixed for PatchTST. It's flexible for Chronos. Multivariate support. I'll talk about that a bit later. Confidence intervals. So PatchTST, it gives you out numbers. There are no buckets and there are no probabilities associated with buckets for the output. So there's also no notion of forecasting confidence. Whereas Chronos, because you have a softmax, you have a probability distribution over which bucket the output is going to be in. That allows you to get a confidence interval over the outputs. Training speed is going to be faster for PatchTST. It's smaller. For fine-tuning, typically you would fully fine-tune PatchTST because it's a small model and cheap to fine-tune. With Chronos, it's a bit bigger. You can lower a fine-tune. It's also not that big, so you could fully fine-tune. For context length, the PatchTST does support longer context because it converts the inputs into patches, so you can fit more inputs than you can with Chronos. And last of all, this is a very rough guideline. I used about 8,000 rows to do training. Probably you need ballpark that amount if you want to do training. And that seems to be sufficient to do full fine-tuning on PatchTST or to do some kind of lower fine-tuning on the Chronos model. The last thing to mention here is multivariate support. So the way both these models work is if you have 2 time series that you want to predict and they're both related, for example, you might have temperature and you might have demand of electricity. Both of these models will treat those separately and they will use the same set of weights. And that's possible because of how those numbers are normalized on the way in. Now, there's a more advanced form of multivariate analysis where the inputs would have cross interactions, which could be cross attention or mixing. And in principle, it seems that would be nice because it gives you more predictive power. What's found empirically in these papers is that having cross interactions tends to result in overfitting. And so you do better by actually keeping the channels separate and only using a given input to predict itself rather than having these cross interactions. But I will show you a parameter you can turn on in the PatchTST model if you want to try out cross attention. With Chronos, there's no way to turn it on, so you'd have to manually introduce it, or you'd have to introduce some cross interactions after making the forecast. With that, I'm going to move to describe how PatchTST works in code and show you how to forecast. And I'll do the same with Chronos, and I'll show you how to fine-tune them both. You can find the scripts on trellis.com/advanced-time-series, and you can purchase access to the GitHub repo either on an annual or lifetime basis. Advanced Time Series is also now included in the new Trellis repo bundle, and I'll leave more details below in the description. Now, I'll also put links to each of the model cards, and you can find links there to other ways of doing fine-tuning and forecasting. So even if you're not in a position to purchase repo access, you can follow along and perhaps build it for yourself with the help of this video. So I've cloned this repo over into Windsurf, and you can see here we're in the time series repo, Advanced Time Series, and there's a README describing the folder structure, which has scripts for PatchTST, Chronos, and then some data. Let's take a very brief look at the data. I have data on the Irish electricity grid. You'll find there's a README description here. And I've downloaded raw data from EirGrid, which is the Irish grid operator. And I've downloaded data for 2024 and also for 2025 to date on a quarter hourly basis. Now, you can use any data for the scripts I'm going to show you today. What you need is to have a CSV that's formatted something like this. Here I have two columns. One is the timestamp in UTC, and then for this analysis, I'll be looking at the load in megawatts. Now, you don't have to normalize just yet because the scripts are going to normalize. So this is my data. I've already shown what the data looks like, and we're now going to ingest that data and run some forecasts. And first, I'm going to run on PatchTST, and I'm actually going to run it locally on my computer because these are fairly small models. So I'll move into the README folder, and I'm going to run this as a Jupyter Notebook. So you could install Jupyter Notebook. You can also just run Jupyter Notebook natively within VS Code or Windsurf or Cursor. If you want to do that, you want to start by moving into the PatchTST directory. PatchTST. Create a virtual environment, activate the virtual environment, make sure you install IPY kernel, and then you can install a kernel with that given virtual environment. It is important to activate it if you're going to install within that kernel, although if you're using the UV command, it's going to anyway install within the kernel or within the venv that you've specified. So actually activating it is probably not critical there. Basically, you just need to create the virtual environment, install IPY kernel, set up the kernel within the virtual environment. And now when you go to the notebook, and this should maybe be called inference and training, you can select that virtual environment right up here. Now, alternatively, if you had already, if you activated the virtual environment, you could run Jupyter Lab, or you could run Jupyter Notebook if you have either of those installed and open that up in your browser. So here I have PatchTST, the virtual environment, and I have my notebook. And I'm just going to move through the setup of this notebook. We're going to start by setting up the environment. We'll set up some parameters that are going to be used for pointing to the data. We'll load and pre-process the CSV so we can make an initial forecast, which I'm calling zero-shot evaluation. This means no training. Then we will do some, I'm calling it pre-training because you could use this to train the model from scratch, although I'm actually going to load a pre-trained model, although it's a pre-trained model for a very different application. And then after pre-training, we'll save the model and finally reevaluate and see if we get better performance. So for environment setup, you need to install transformers, parameter efficient fine-tuning if you're going to do LoRa, accelerate for device management, and then if you want to quantize, you could use bits and bytes. I'm not using it, but you could install bits and bytes. And you also want to install, there are some helper libraries available. This is a library by IBM, and IBM has trained a model that's called Granite, and it's a model that's specifically trained to predict the temperature of transformers. And I don't mean LLM transformers in this case, I mean electricity transformers, actually from China. There's a large data set of the temperature patterns of these transformers. And this is a model that's been specifically trained on that. So we're going to take this model for electrical transformers, and we're going to see if it does any good on predicting the demand for electricity, which I suppose there's some kind of relationship between the two and maybe some similar patterns. So maybe that'll help. But broadly speaking, these are different applications. So after these installs are done, we're going to set the device. The device I'm using is MPS. You could run it in Colab and use a GPU if you want. You could run it even on CPU. It'll be just a little bit slower. And next, we're going to set the configuration for running the notebook. And we're going to run the notebook twice because we want to run it first on this pre-trained model. So we want to run it on the IBM-granite model, but then we want to load a model where we're going to fine-tune it specifically for our application. So I'll do the first case first. I'll comment out this pre-training one and set up the granite parameters. I need to point to my hourly data, so I'll point to my CSV for that. I need to indicate the timestamp column, and I need to indicate the target column. The target column refers to what we want to forecast. Now, there's this further feature here, which is called ID columns. This is if you have extra columns that will describe kind of subcategories for your data. So for example, I already have 2 columns, but I could have another one that additionally lists the region. So it could say Europe, China, US, and there would be a label for each of my rows. And if that's the case, what is going to happen in data prep is my series of data, which is just one column for demand, it will be split into a separate series for demand for Europe, demand for US, demand for China. So this just allows you to kind of get some splits on that data. Next is context length. So this is the input length. And actually, you don't have flexibility if you're using the pre-trained model. You have to use 512. And you also don't have flexibility on the forecast horizon. So we're going to have 512 input timestamps, and we're going to have 96 output timestamps. Now, if you want to predict, we're predicting here hourly data. If you want to predict daily data, then that means, ideally you have almost 2 years worth of data. And your forecast horizon is going to be 96 no matter what. When we fine tune the model though, or when you pre-train it from scratch, we're going to be able to set it to parameters we actually want. And the parameters I'm going to want are 1 week. So I want to make prediction based on 1 week of prior data, and I want to forecast 1 day ahead. So that's 24 hours ahead. Last of all, we can set the training fraction and validation fraction. The remainder is the test fraction. So the training fraction will be used for pre-training the model. Then we're saving the last 10% in this case here as the test fraction, which we'll use to measure performance. And then the 10% before that we're going to use for validation. So yeah, basically it's best practice to have a separate split for training, for eval, and for testing. Why do you have a different split for eval and testing? Well, the eval split you typically use to look at the loss curves when you're doing the training, and you're going to make decisions on hyperparameters based on the loss curves. So you're going to pick the best model based on your eval loss or your validation loss being minimum. But then to be independent of that choice, you want to have an other split yet again called a test split that allows you to measure kind of independent performance of that specific choice you've made based on the eval set. Okay, that was a bit of a granular comment. Back to running this script. We've got everything ready. We're not going to train it, but this will still define a test split for us to run the analysis. Next, we will load the CSV. So we're just reading in the data frame, and we're doing the splits of the data, as I just said. And now we're going to pre-process. And there's a little helper here. This is why we did the installation from the IBM library. There's a time series preprocessor, and it's going to help us to pre-process according to our columns that we've defined. And it's also going to do scaling of the data. So here we're using standard scaling, which means we are subtracting the mean of the data and then dividing by the standard deviation. This is going to be good if the data is roughly normally distributed. I'm not saying this data is normally distributed, so maybe it's not the best choice. If you wanted something a bit more robust, you could use something like IQL, interquartile range, which will use the quartiles and is more agnostic to the shape of the distribution. Later, we're just going to do mean scaling, which means there's no scaling of the width of the distribution, and all of that variance in the width has to be modeled. It has to be captured by the model itself. So depending on the type of scaling you do, you're basically putting more load on the model to be able to cover up for that or not. Typically at a minimum, you do mean scaling. The other nice thing about mean scaling is it maintains zeros. So any zero in the original data set, when you divide by the mean, will still be zero. By contrast, in standard scaling, you will always subtract the mean from each data point. So any zeros in the data are going to move usually to negative data points if the mean is positive. And often there's a specific meaning to zero. For example, zero in the case of operations or outages, that just means nothing is happening. And there might be a lot of zeros in your data set, and keeping it at zero can often be a good idea. And that's why mean scaling can be nice, because it has that property. Okay, so we've processed the standard, we've processed the data set here. We've got about 8,000 training rows and 1,000 validation and test rows. Okay, next, I'm going to define this function here called compute metrics. It's basically allowing me to calculate a few of the parameters we care about, like the mean average error, which is calculated by taking the average difference between the forecast and the ground truth. Then there's the root mean squared error, which is a squared version of the error. And then there's the mean average percentage error, which is the percentage error at each time step, then averaged across that interval. So I've calculated compute metrics. You'll see where we use that later on. And I'm also going to, and when I say calculate, I mean I've defined the function. And I'm also going to define a function here to evaluate and visualize the data. And the way we'll evaluate, this is kind of different to a lot of my other videos. We're going to make use of the trainer to run the evaluation. So we'll set up a trainer with a given model with training arguments, which really are just the output directory and the label names, which we're just making up to be future values. And we'll get predictions by running trainer.predict on the test data set. And we'll take those predictions and we will then rescale them. So we're going to use the inverse transform method as defined in compute metrics. So we need to match that. And we're going to scale them back to the original values, because remember, the model is working with normalized values. And then we'll compute the metrics that we care about here. Now, this is kind of nice that there's a library from IBM that allows us to define the scaling, because it means we can use the same scaler for both scaling and for inverse transform. So that's for normalizing and backwards normalizing to get back to the original. And it's always good to use the same library, because that means you're not going to make mistakes in having a different transform in each direction. Unfortunately, we don't have that when it comes to Chronos, at least not the way I did it. But we'll find a way to figure it out. Okay, so we've defined that evaluation. And now we're going to do zero-shot evaluation. So we're taking this electrical transformer model, PatchTST model, and we're going to then use it and see if we can predict the demand of the Irish grid. Now, there's one other change we have to make, because that model by default takes in 7 channels. So it's actually predicting 7 attributes of those electrical transformers, whereas we're only trying to predict one single attribute, which is just the demand. So we're going to have to change the configuration to just use one input column. Now, there's no mixing between the columns, so this isn't going to cause any loss in accuracy. We'll pass in that modified configuration, so we just have one column that's being treated. We'll pass in the base model name, which is this ibm-granite model. We'll move the model to the device, which is MPS for Mac, and we will move it into the data type, which I think will be float 32 right here. So I think I've run all of these. I've basically loaded the model now. If you wanted to, you could at this point decide to print the model and see the architecture. So you can see here, it is a transformer model. We have a patchifier, and then we have an encoder, which has an embedder, a positional encoder, and then it has layers. So it looks like it has 3 layers. And those 3 layers have got attention, and they've got these linear layers with GALU. These are kind of MLPs, multi-layer perceptrons. And then we have the head, the prediction head. This takes the embeddings at the top of the model, it flattens them out, and then uses a linear layer to predict the outputs. And you can see this model, it actually predicts 96. So the paper has got a default of 64 outputs. This IBM model has got 96. And the model we're going to train is just going to have 24, because we want 24 hours. All right, so we can evaluate. And looks like we've hit some kind of error. And yeah, the input sequence length doesn't match the model configuration. And that's because the data that I set up has got, it's got inputs of 1 week of data. but we can fix that actually by padding the data. And yeah, actually, let's pre-process with padding instead. Okay, so we've pre-processed with padding, print the model and evaluate. And you can see that has fixed the issue. So yeah, we actually do need to pad because the way I've set things up is I'm just using inputs of 168 data points, but the model expects 512. So I need to do padding. And you can see even with that padding of the left-hand side, the model is, pretty good. This is just visualizing one specific output. But you can see that it's definitely representing the shape a little bit, sometimes over-predicting, sometimes under-predicting. And the mean average percentage error here is about 7%. The absolute error is about 378 megawatts relative to a mean value of somewhere around 4,000 to 4,500. So this is the evaluation. We actually have the stats as well across the full test set. Actually, I don't think this is the full test set. This is probably just the evaluation over that single data point. No, actually, this is a summary of the results across that full test set. And then we just plot the first sample IDX here. So you can see the error, 7%. But this is pretty impressive given that it's a temperature, it's an electrical transformer model that we've then applied to predicting the power demand of the Irish grid. But let's see now if we can do better than that. And let's see if we can do better by fine-tuning the model, or rather training it. Now, I say training the model, pre-training, or doing it from scratch. And that is true because here I'm actually loading just a base configuration and defining a raw model with random weights. Whereas you could actually try and load the model from the electrical transformer, and maybe that would give some kind of benefit or speed up, but I'm actually training from scratch here. So I'm going to go up to the top of my script and I'm going to change this because I want now to have a model that is going to be for a context length of 168 and for a forecast horizon of 24. And I'll keep the patch length the same. My batch size for training will be 32 and my number of workers, number of CPU cores used for data processing is 8. It's going to be really fast, so you could just set that to 1. It will be fine as well. So I'll set that, load the data. I'm not going to do any pre-processing with padding. That's not needed because my model's now going to expect 168, define compute metrics, define the evaluation. And now I'm going to instantiate my model. So for that, I'm going to define a PatchTST model that has these parameters here. You can see, for example, the embedding dimension or the model dimension is 128. That's the width of the matrices. If you make that larger, you're making a bigger model. The number of attention heads, the number of hidden layers. I think that's the feed forward network dimension. Dropout means some of the weights will randomly be dropped on forward passes to try avoid overfitting. Some of the heads will be dropped out 20% at a time. And yeah, there's one parameter here called channel attention. And this is the parameter that you set to true if you want channel mixing. Generally causes overfitting. So yeah, just be aware of that. But this is where you would allow the inputs to kind of interact if you want to have the interactions affect your prediction. For the loss, we're using mean squared error. And yeah, we're using pre-norm and norm type. The batch norm is apparently better than layer norm for these time series models, but I haven't looked too much into it. Okay, so once we've defined the configuration, we load the model, we move it to our device, and we move it to our data type. It should be float 32. And yeah, we're running on MPS in float 32. Now, at this point, if you had a pre-trained model, which, by the way, you could load by running this line instead, which would just directly load the base model. So if you had directly loaded the base model, you could decide to add a LoRa adapter. Why would you do that? It will train faster, but that's not a big deal because it's a tiny model. But also LoRa tends to overfit less. So you might want to use LoRa. You would do that by importing the LoRa configuration. defining which layers you want to target with these adapter matrices, and defining what the rank is, the LoRa alpha, the dropout. So this isn't something I've tested just because the model is small and typically you can just run full fine tuning. So here we'll run with the training arguments. We'll use a learning rate of 1e-4. We're going to train for 5 epochs. I think I just took the defaults for this. It's kind of a surprisingly low learning rate given the model is so tiny. But yeah, it seems to work fine. Batch size is 32. We're going to save every epoch the model. We'll log every epoch as well. We'll load the best model at the end. Now, there's an interesting way this is set up, and it's an interesting idea I could use for later videos too. Basically, this is using an early stopping callback. So it's going to train the model until there's no improvement in the evaluation loss. So you could put this number of epochs to something much larger, like I think 100 is the default. And it won't actually run 100 because it'll just plateau and then it'll automatically stop. So that's kind of a cool feature, but I've just hard coded it to stop at 5 epochs. So with that, we'll run the training, and running on Mac here. It will take a little bit of time. And yeah, just while that's running, once it does run, we'll get the output from running trainer predict, which is just running a prediction on the test dataset. And we'll check the output shape. The output shape should be the number of rows in the training dataset times the number of predictions, which is 24, because that's what we asked for. And then times 1, because we're just predicting one time series. So we'll check that's correct. We will save the model then. You could optionally push it up to Hugging Face. And then we'll reevaluate it just by running that evaluation function from earlier. And what we're going to find, spoiler alert here, is that we do get a significant improvement. So we were at, I think, 7%, and now we will hopefully be down somewhere around 3% for the mean average percentage error. Now, just a warning, mean average percentage error can be quite noisy. If there are any predictions that are close to 0, then you get very wide variance in the error at that point, and so it can affect your mean average. So you could look at it instead at the mean average error, which is an absolute value, 141. And yeah, I mean, it's really doing a good job here of following the pattern, and the error is pretty low. So what I'll do is I'll just let that run out. I'll make sure to press enter on these lines here. I'll save the model and run a reevaluation. And we can see in the meantime, we will soon have run one evaluation. I'm going to start up TensorBoard. I should have pointed out that in the training configuration here, I think I have report to TensorBoard. Do I have it? No, I actually don't have it set up. I'll show you TensorBoard in the next script. But if you do want TensorBoard, you would just put in report to TensorBoard like this. And you would also need to install TensorBoard. So you do uv pip install TensorBoard, QU. And by the way, if you're running on RunPod or something, you'd put in system to install it on the system. Just running this will run it in the virtual environment. And yeah, this is your logging directory here. So it'll be this directory here. So if you want to run TensorBoard, I'll just write it down here. You would basically do uv run in your terminal, uv run TensorBoard, and then logdir, and then you need to point to that logging directory. Also, something I like doing if I'm logging to TensorBoard is I like putting in kind of a run name here. Often I'll, hard code some manual run name, or else put in the time and the date, just so that you have a different folder for each of the runs that you want to put in. So what I'll do is I'll just leave commented out for now the use of TensorBoard, and you'll see exactly how I use it in the other script. Okay, so yeah, in the meantime, you can see an output here. We have the training loss, the validation loss. Training loss is lower than validation, which is generally a good thing. And, well, not a good thing, but an expected thing. If the validation is a lot lower than the training loss, then it means your data is very unevenly distributed. Somehow you're performing better on the eval split. But we can already see that both are falling, and the mean average error is falling as well. All the metrics are falling here. And from the value of 7, you can see that we're going down, and we'll probably end up somewhere around 3. So yeah, this is a a quick demo of how the PatchTST model works. I'm going to move on and show you now the very same, but for the Chronos model, where we can do zero shot and hopefully get a lot better performance. And then I'll even fine tune the Chronos model as well. So let's move over now to the Chronos folder and open up Chronos training. And just as I did for PatchTST, you want to set up a virtual environment. Make sure you install a kernel within the virtual environment, and then you'll be able to select it up here. So I'll select Chronos, and we'll work through the notebook. So a few things here in this notebook. We'll load the data, prepare the splits, and visualize a forecast, zero shot. We'll prepare for training. We have to prep the data. And after preparing for training, we will be able to run an evaluation, which we should see right here. Yeah. So maybe I'll even just add in a quick section here that just says run evaluation. And yeah, now we have a few nice sections within the notebook. So the very start, we're going to run an installation. We need to install Chronos Forecasting. That's an Amazon library. Also parameter efficient fine tuning, so we're doing LoRa, transformers, accelerate, datasets. We'll use Hugging Face datasets. Evaluate, bits and bytes, and TQDM, which shows you progress bars. So we'll run that. I think I've already installed it. I can run it again. And next we'll select our device. So same as last time, MPS, it'll be float32. I think actually that BrainFloat16 might be supported or supported kind of indirectly. So right now I'm defaulting to float32 if it's not on CUDA. By the way, if you're in a T4, you can't use BrainFloat. You have to use float16. So just a note there, T4 is like the free Colab notebook or Kaggle. Next, we'll define the CSV path, the timestamp column, the target column. The context length and forecast horizon will keep the same. The training and validation fraction will keep the same. The patch length here is actually irrelevant because there is no patch. The batch size 32 and the number of workers will be 8. So here we're going to read in the data set. This is actually the exact same as the other notebook. We're just loading up and splitting the data set so that the last part is the test data, the most recent. Then we have the eval, and then the earliest history, 80%, is going to be the training data. And what we're going to do is create shorter examples then that are of length 168, which is the input, plus 24, which is the forecast length, so 192. We basically have these long chunks of data, and we need to split that into smaller examples. And the way we do that is by taking, basically taking a window of 192 and sliding across it with a stride of 1. Now, we don't have that much data, so we use a stride of 1. If we had a lot more data, maybe you could use larger strides because there would be just a lot of redundancy in the data. But when you don't have a lot of data, you can use a smaller stride. And so we have a function here called create datasets that's taking in the data frames. It's taking in information on the context length and the forecast horizon. That's the 168 plus 24, so 192 total, and then striding by a stride of 1. So we can run that, and it's going to convert it into now data sets. So we have a data set for training, which is about 7,000 rows, each of them 192 numbers in it. Then about 1,000 rows for validation and 1,000 then for the test as well. So next we're going to load the data, or rather I've already loaded the data. So we're going to load the model and visualize a forecast. The model is going to be Chronos T5 small. You could try out a larger model if you want to see better performance, or a smaller one if you want faster performance. So we can load up the model, make sure that matplotlib is installed so we can visualize. We'll define a generate and visualize function. So this is going to create a tensor for the context. So that's the 168 inputs, create a tensor for the output, and pass them into a pipeline for prediction. So this is a function here, the pipe, that has taken in the model. You can see the pipe is defined earlier. In fact, it's just passed into this generate and visualize. We'll see how the pipe is defined. And then we forecast using pipe.predict. we can calculate some of the values here, the different ones we like mean, average, error, and then we can plot. Now here I'm just doing it on one single data point, so I'm not doing it on the full test data set. So just be aware of that. I'm just running a quick example. And here I'm going to evaluate. So I'm actually running the function above now, but passing in pipe. And we'll just take a look at where pipe is defined. And yeah, you can see actually when I loaded the model is being loaded through the pipe. So you pass the model ID into pipe. It's a Chronos pipeline. You need to define the model, the device, and also the torch D type, the torch data type. So with that, we can run generation. And this is just running generation on one example. And yeah, I've chosen the first example in the training data set. And here we go. You can see our mean average percentage error is 1%. And this is zero shot. So we haven't even trained the Chronos small model, but we have very good performance. And furthermore, you'll remember Chronos can do the confidence interval because it's predicting a distribution over buckets. So this is the 80% confidence interval, and pretty much all of the actual values are falling within that 80% confidence interval. So this shows you how well a model is doing when you just have zero shot on Chronos. It's not even fine-tuned for this specific application. Now, Chronos is trained across a very wide variety of applications, time series for, I think, traffic, healthcare, power, maybe finance. It's got a very wide range of data, and that's why it's able to generalize quite well. So with that done, we'll see if we can improve performance more by doing some training. So to prepare for training, we will need the tokenizer to help us format the data. Basically, we will take the tokens. We need to, or take rather the numbers, the quantized numbers, convert them into tokens, and then we will need to prepare the tokens into the proper arrays with some beginning of sequence and end of sequence tokens. So just here, I'm going to make sure the tokenizer has got the correct forecast horizon and context length. It's actually a bit surprising to me that's defined in the tokenizer, but it is. So I need to update those. If you want to learn more about the tokenizer, you can do print and then help and then tokenizer. This is helpful just because it tells you what different functions are available, notably label input transform. This is the transformation to do the quantization, and the context input transform. So these are going to be useful. Output transform then is to reverse that. So we're going to be able to make use of these when we want to tokenize or detokenize. So then I've got a function here to process the data set. And yeah, what this is doing is it's splitting and encoding each example. So it's taking each of those 192, splitting up the 168 and the 24, and then it's encoding the first part so it can go into the encoder because this is a T5 model, and then it's encoding as well the second part, the labels, because that's basically what we're going to measure the cross entropy on. So we're going to get some outputs from the model and compare those to the tokenized tokens that will come from the decoder. So I'll run this here, the prepared data set. We're going to run it on the training set and the validation set and the test set. And should just take a few moments. And we have a data set here of about 8,000, 1,000, 1,000. And now we need to handle padding and batching. So if there are any sequences that are less than the required 168, we will left pad them. And we also will make sure that we have batches that are going to contain the input IDs, attention mask, because this is autoregressive. It's a causal model that can only look backwards. It's not able to see future tokens. And it also needs to have labels because that's how we evaluate the cross entropy loss. And we can now move on to training. So we basically have the data set ready. We have a data collator defined, which is going to take the data and feed it into the trainer. We are now going to load a model. And this is the base model. So it's the same model we ran already. We're going to make sure the model has got the context length and forecast horizon defined as we want. So we set those here. And now we're going to evaluate the model. So I did show you an example up here, just on one example. This is just the first data set point. But actually, I want to get the metrics across the full training set. So I'm going to run evaluation on the full test data set rather, just so we have a baseline of what the the mean average error is, so we can compare it before and after training. Now, while that's running, we'll apply LoRa. So we're going to take the model and we're going to apply adapters. We'll apply adapters to these target modules here. If you want to check out and figure out the names that you should use for the target modules, you should print the model like this. And when that prints out, it will show us these names and we'll find that we can train these modules. You can also train the embeddings. I don't think training the embeddings is necessary here because we're not changing the tokenizer. But if you did change maybe how you're normalizing to a log basis or exponential basis, something very different than the normalization used for training, for pre-training the model, which was mean norm, then you might want to pre-train or retrain the embedding layers. So embed tokens in LM head, which is the reversal of the embeddings at the top of the model. So with the LoRa adapters applied and training these embed tokens in LM head, about 15% of the total parameters will be trainable. The backbone of the model is frozen, and we can move on to training. So we're going to train with a cosine scheduler. So the training rate will fall during training, starting at 3e-3. Batch size at 32. We'll just train for 1 epoch, and we will log every 50 steps. We will evaluate every 20% of the full run. And yeah, I've got 25 warm-up steps here. That's probably not important. And here you can see I'm passing in the training and the validation dataset. And that should instantiate the trainer so that we're ready to run a training here. And you can see I've run this already with the training. You can see how the training loss goes down here, 1.92 all the way to 1.45. And the validation loss, unfortunately, does not decrease that much. It goes from 1.72 to 1.67. If you check the values here of the mean average percentage error, it is going down, so that's good. The mean average error is going down as well. But yeah, really the performance is not improving all that much. If you want, at this point, you can look at the training dynamics because you can see I've reported to TensorBoard. So if you move to the Chronos folder like this, you can do UV run TensorBoard and then logdir logs. And if I open up TensorBoard, I should be able to see some of the runs from yesterday. And I think one of the last runs was probably this one here. So you can see the eval loss is falling, but it's falling very slowly. You can check all of the losses here are falling, but they're falling very slowly. The gradient norm should be showing here. Always you want this to be below about 1. So the training is stable. And here you can see training loss. So yeah, here are some examples of the training loss curves. Again, this is falling meaningfully, but unfortunately not really translating to the validation loss. So if we go back here to the model, we can save the model, optionally push it to Hugging Face, and then we can run evaluation again on the test data set. We can run it just on index 0 for visualization. And here you can see the mean average percentage error is 1.78. It's actually higher than what we got above, which was 1. But this is just one data point. So you don't want to base your judgment on one data point. You want to base it on the full test data set of about 1,000 points. So for that, we can run the evaluation on the test data set and we can see what kind of performance. And yeah, based on that, we're seeing the mean average percentage error is about 2.87, which is to be compared to the mean average percentage error that we ran just before doing the training, which you can see here is 2.88. So there's a very small improvement in performance from, if you take MAE 119.15 to 118.68. So I don't even think that's statistically significant. Perhaps if we had more data, so I've just trained on, say, 1.25 years, maybe if you trained on 5 years, you might be able to improve that a bit more. But on the other hand, because this model is so general, it probably is able to generalize in a way that's very strong, and adding this fine-tuning data is not really helping a lot more, because if we were to force fit it, it might even disimprove performance if the model starts to overfit. So yeah, in the meantime, I think I can show you some of those results from that evaluation. In fact, I just did the evaluation completed, and yeah, it was 2.88. So basically on the Chronos model, it performs very strongly just on 0 shot. You can consider fine tuning. Maybe if you have a lot of data, that makes sense. or if your model is from a domain that may not be included in Chronos, Chronos probably includes some electrical demand data already, and that's maybe why it's performing well. So you may or may not see all that much improvement, certainly not as much improvement as the PatchTST model. Now, just let's go back to the PatchTST model because I was still running the evaluation when we finished that off. And we can check our results here now. We reran on the fine-tuned model, and yeah, we got down to 3.28. That just matches the run that I showed from earlier, pretty much. So you can see the performance going to 3.28 rather than the earlier performance, which I have here in the zero-shot evaluation of 7.29. So yeah, basically using the electrical transformer model, which is off domain, got you 7.29, but pre-training from scratch got us down to around 3%. So we got a significant improvement in the PatchTST model. And that rounds up the overview of PatchTST and Chronos. I think the performance is quite impressive on both of the models. PatchTST significantly faster. I could see it having benefits if you need to run a lot of forecasts very quickly. But Chronos, on the other hand, I think very generalizable. If you need to quickly assess whether forecasting is going to work well with transformers, probably running the Chronos model is going to make a lot of sense, especially because you can try out the model at different sizes and see if you can improve performance while trading off latency on that front. I'll put a link to the materials I covered today in the description, and you can find the scripts if you want to purchase repo access on trellis.com/advanced-time-series. And in the meantime, if you have any questions, as usual, put them down below in the comments. Cheers.